So in the previous two sections of this chapter, we talked about general considerations for the transmission line, what is a transmission line, why we need it, and the lumped element circuit model. Let's start this section, transmission line equations. A transmission line usually connects a source on one end to a load on the other end. So here we have a source, and here we may put some sort of load. Before considering the complete circuit, however, we'll develop general equations that describe the voltage across and current carried by the transmission line as a function of time and spatial position. So we just took a small part of this previous model. We took one of those parts, and then we will discuss the voltage and current across it. Using the lumped element model of figure 2.6c, we begin by considering a differential length delta z as shown in figure 2.8. The quantities V and I denote the instantaneous voltage and current at the left end of the differential section, node N, so right here. And similarly, V, Z plus delta Z, T, and I of Z plus delta Z, T, denote the same quantities at node N plus 1, located at the right end of the section. Application of KVL accounts for the voltage drop across the series resistance and inductance. So we will do a KVL for this loop, and it accounts for the voltage drop in this. So the voltage here minus the voltage drop equals 0. So let's see how we'll get it. So V of Z and T, this one, minus the voltage drop across R, which is R prime, which is resistance per unit length, times the length, which is delta Z, times the current, will give us the voltage drop across the resistance, minus the voltage drop across the inductance. As we can remember, the voltage drop across inductance is V equals L di by dt. This is what is happening in here, minus the voltage at the end equals 0. Upon dividing all terms by delta Z and rearranging them, we obtain this equation. And as delta Z becomes really, really small, we could see that this one becomes a derivative. So this whole equation is just a differential equation. Similarly, KCL accounts for current drawn from the upper line at node N plus 1. So KCL accounts for current that goes here by the parallel conductance and capacitance. So the current coming from here is divided into two parts, a current going in here and the other one going in here. So this one minus the current going in here minus the current going in there equals 0. So I for the source minus this part. How is this the current? So as we know, current equals voltage over resistance, impedance, or whatever, but G here is an admittance. So admittance is Y equals 1 over Z. So here this equation becomes I equals Vy. So that's why we multiply the voltage by the conductance. So for C is I equals C dV by dt, minus the current at the end equals 0. Upon dividing all terms by delta Z, the same thing we did previously, and taking the limit delta Z tends to 0, we also get a differential equation. The first order differential equations are the time domain forms of transmission line equations known as the Telegrapher's equations. So this is what we were talking about earlier, and we needed to reach them. Except for the last section of this chapter, our primary interest is in sinusoidal steady-state conditions. To that end, we make use of phasor representation with the cosine reference as outlined in section 1.7 in the previous chapter. So the voltage is the real part of the phasor voltage times e power j omega t, and I is the same thing but for current, where this thing and this thing are the phasor counterparts of V and I respectively, each of which may be real or complex. Upon substituting in equations that we did previously and utilizing the property that d by dt in time domain is equivalent to multiplication by j omega in the phasor domain. So it's telling us there's a property that derivating in the time domain leads to as if we multiplied by j omega in the phasor domain. We obtain the following pair of equations. So we just substituted by the voltage, and instead of the derivative we multiply by j omega, and just going on by the steps, we finally reached the telegrapher's equations in phasor form. The next section is wave propagation on a transmission line.